been working at. So again, what we've been talking about the last several lessons has been solving trigonometric equations. We started by just talking about how to find solutions between 0 and 360. We talked about how to extend that to finding all solutions. And then we talked about, okay, how can we now make the solving process a little bit more algebraically complicated? And that's kind of where we're at now, is we're just going to do a day of examples of some of these more intricate solving problems. Stop talking, please. Thank you. So let's first look at this example of sine x tan squared x equals sine x. So notice here we have more than one type of trig function, right? We have sines and we have tangent squareds going on in here. For almost every single one of these, what you're going to want to do is you're going to want to start by getting everything onto one side. So I will just subtract sine x from both sides. Everybody okay with to there? Okay. Now if I look here, this looks like there are two terms. There's this term and then this term. Everybody kind of see that, where I have two distinct things? Do you notice anything in common between these two things? There is a sine x in common, so let's factor that off. Everybody okay there? Now that this is, thank you, it's okay. That this is in factored form, I can apply the zero product property. And it's okay to do that because you'll notice that each factor has only one kind of trig function in it. Does everybody agree with that? So I can say sine x equals 0. And then tan squared x minus 1 equals 0. Nope, we did not cross anything out. What we did is we applied the zero product property and took each piece, or each factor, and set it equal to 0. And now we're going to take this complicated problem and break it up into two less complicated problems. Everybody's okay with that? Okay. So to solve sine x equals 0, what do we need to do? Sine inverse to both sides. And hopefully you recognize sine inverse of 0. Where can I find that value? On the unit circle. Everybody agree with that? So if I go to the unit circle and I'm looking at, for sine, which coordinate am I looking for? The x or the y? The y coordinate. So I'm looking for the places where the y coordinate is 0. I see that happens when the angle measure is 0, and also when the angle measure is pi over 2. Not pi over 2, I meant pi. Jeepers creepers. And if I go around my unit circle again, I see that I get 0 at 2 pi, but I'm not going to write 2 pi down as an answer. Why not? Yeah, so if I look at the directions here, it says I want my answers 0 less than or equal to x less than 2 pi. So I should not include 2 pi, so that's going to be it from that piece. Everybody happy there? Okay. Now let's look at the tangent squared piece. So how am I going to solve this tangent squared minus 1 equals 0? I'd start by adding 1 to both sides. And the next thing I would do is square root both sides. When I square root both sides, though, what do I have to remember? Plus or minus. And because of the plus or minus now, I'm going to split this up into 2 different problems. Everybody okay with why I just did that? And how do I solve tan x equal to 1 then? Tan inverse. Now, tan inverse of 1, is that a unit circle value? Yes. What is tangent again in terms of sines and cosines? It's sine over cosine, and sine is x or y. Y, cosine is x, so for tangent we're looking at y over x's. So if I want y or x to be 1, I'm looking for specifically when x and y have the same value. Everybody okay with that idea? So if I go on my unit circle, I see that happens when we have pi over 4. And then it happens again at 5 pi over 4. Everybody okay there? Okay, let's do the same thing for tan x equals negative 1. So for that, I need the x and y to be the same thing, but opposite signs. So I notice that happens at 3 pi over 4 and 7 pi over 4. Everybody okay here? So we're almost done. There's one thing, though, that I need to check. And this happens whenever you have a tangent inside of the problem you're solving. So remember what the graph of tangent looks like? Does anybody remember? It kind of looks like this. What are these little dashed lines called again? Those are asymptotes. Why do we get those asymptotes? It's where the tangent function is undefined, right? Everybody kind of remember that? That sometimes when we do tangent, we get undefined as an answer. What I need to check is to make sure tangent is not undefined at either of those 2 places. Because if tangent is undefined there, it doesn't matter if sine x is equal to 0 there. This equation will be undefined and not 0. So that's the last thing I need to do, is I need to check. So remember that tangent is y over x, right? So I need to look at the places where x is 0. That happens at pi over 2 and 3 pi over 2, neither of which are these, so all of these answers are okay. So again, I'm checking to see the places where tangent is undefined, and I'm making sure those aren't some of the other solutions that don't come from tangent. Since they are not, those answers 0 and pi are fine. If I had answers that were undefined, I would discard them. Is everybody okay with that idea? Okay. Let's do another example solving one. So let's say we have 3 sine x equals 2 cosine squared x. Okay, so what do you think the first thing I should do here is with this one? In order to solve these things, eventually this has to be equal to 0 is usually what we want. So I think maybe the first thing I do is just subtract that 2 cosine squared from both sides. But now it seems like we're kind of stuck, right? Can I factor anything here? No, right? What's getting in the way? That my trig functions aren't the same kind of trig function, right? So what should I do here? I think Sophia has a good idea. Is you're going to go to your identity sheet and you're going to ask yourself, is there a way for me to rewrite cosine squared in terms of sines? Does anybody see a way to do that? Cosine squared is 1 minus sine squared. And then let's go ahead and distribute that -2. So you notice that I've just written things in that different order there. So I wrote it kind of in a standard form. And if we look at this now, this kind of looks like something to me, right? That if I pretend that sine is equal to y, this thing looks like a quadratic equation, right? Everybody's good to that? So how do I factor, or how do I solve a quadratic equation? You could use factoring, right? What else could you do, though? You could use the quadratic formula. Does it matter which one you use? Nope. Since this is factorable and it's that kind of sneaky kind of factoring, let's go by, or let's do it that way and review how to do that again. So to factor something, you need to find two numbers that multiply to give you a times c and add to give you b, when we mean that a, b, and c are the coefficients of that quadratic, right? So in this case, a times c is -4 and b is 3. Does anybody see two numbers that are multiplied to give us -4 and add to give us +3? Huh? So this is the procedure for factoring, is all this is. I think you mean +4 and -1. Right. Good. Agreed. Everybody's good with that? That sees that satisfies those two requirements. So what do I do with these two numbers? I'm going to replace that 3y, and I'm going to write it as 4y plus a -1y. Now notice that polynomial that I've just written is exactly the same as the polynomial before it, right? If I just add the 4y and negative 1y, I'm back at 3y, correct? So I haven't changed anything. I've just kind of broken it up into a new form. What I'll do now is I'm going to make two groups. From the first group, what is the greatest common factor there? 2y. And from the second group, I have a greatest common factor of negative 1. And now you'll notice that each of these pieces has a y plus 2 in common with it. So if I factor the y plus 2 off, the stuff that's left is the 2y minus 1. Everybody okay to hear? I've got this into a factored form, so I can now apply the zero product property to rewrite this as two separate problems, each of them equal to 0. And then if I subtract 2 from both sides of the first one, I have y equals negative 2. And if I add 1 and divide by 2 for the other one, I have y equals 1/2. Am I finished? No. Remember that I wasn't trying to solve for y, I wanted to solve for x. What does y equal again? Sine x. So what we can do now is put that back in. And now how do I solve sine x equals 2? Sine inverse. Is 2 a unit circle value for sine? Negative 2, thank you. Is it? No. So what do? Go to the graphing calculator. If it'll ever load, there it goes. Okay. So sine inverse negative 2. And if I press enter, did I do something wrong? Okay, so you think it's the mode's the issue? So I'm in radian mode. What if I try it in degree mode? What's going to happen? Same problem. So remember, what does the graph of sine look like? It looks like this, right? What is the highest value it has? 1. What's the smallest value it has? Negative 1. So the inverse is going to take values between 1 and negative 1 and map them back to an angle, right? This just has no solution to it. There's nothing we can get from that. That's not going to contribute any answers to us because my value that I'm trying to take the sine inverse of is outside of the range of sine. So there is nothing we can do with that part. So there's no solution coming from that piece. Is everybody okay with that? So if I try to do sine inverse or cosine inverse of something that's outside of the range from negative 1 to positive 1, you're going to get an error on your calculator. And all that's saying is that that part of the equation is contributing no answers. Is everybody okay with that? Important to remember, though, tangent, you can take the tangent of anything. So you got that going for you. So this one, again, we'll do sine inverse of both sides. And positive 1/2, is that a unit circle value? Yes. So if I go to my unit circle, where is sine equal to 1/2 at? Pi over 6 and 5 pi over 6. Okay. I was like at 5 pi over 3, I think we're... Oh, that's positive, so that's the cosine. Yeah. So that's it. Oh, I mean, it was a lot of algebra to get there, but it wasn't, the solving the trig part wasn't so bad once we got into a form we could handle, right? Let's do another one. So, you guys remember how we had been saying here that we should that we had been wanting to get it equal to 0? What if I have something like this? This is one of those few occasions where I'm not going to want to do that. Is there any way for me to change sine into something with cosines in it? Doesn't look like it, right? Is there any way for me to change cosine into something with sine x's in it? Does anybody else hear that hum? What the heck is that? That thing does this every day? Weird. Okay. Fair enough. I said, oh. We observed that there was no way or nothing on our sheet to turn sine x's into cosine x's or cosine x's into sine x's. Hopefully, right? Here's what I'm going to do instead then. And you're usually not allowed to do this, so don't get in the habit of doing this, but in this particular case it's okay. I'm going to divide both sides by cosine. Now, what's the advantage of doing this? And what is sine over cosine? Tangent. Aha! That's good, because we can deal with a single trig function, right? So we just do tan inverse of both sides. Is tangent of 1 a unit circle value? It is. I believe we actually even did this earlier. If I scroll back up here, look at that. Tan inverse of 1. We did it already. Pi over 4, 5 pi over 4. And you thought it was going to be hard. Ha! What do you guys think? Do you feel okay doing this? Yeah? You just ready to do something else? Okay. So, let's give you some practices then. And he was going to do it anyways. You're correct. So, for next time, 411, 51 to 61 odds. Sure. I know. What are you going to remember to do for me, though? No, you're supposed to say swim fast. Swim fast. Yo.
I am not here Monday and Tuesday.
Okay.
So, what am I going to